Differentiation, one of the most critical skills in calculus. But let me ask you, have you ever looked at a problem and wondered, should I use a product rule here? Or maybe the chain rule? Wait, and what about the quotient rule? If you ever felt stuck, you are not alone. In this video, I'm going to take you step by step through some carefully chosen examples. And here's the best part. I won't just show you how to solve them. I'll explain the decision-making process, and you'll learn how to choose the right rule. So grab a pen and paper, follow along with me, and make sure you stick around until the end, because I can assure you that if you do, differentiation will become easier than ever. If along the way, it feels like the foundation of your understanding of the key 3 rules in differentiation is still a bit weak, then I suggest you check out the differentiation playlist that I put in the description. But don't forget to come back here. Alright, let's jump in. Now let's start from the easy one first. Here we have to differentiate the expression of x squared times e to the power of x. So in the first glance, you can see that this is a product between two functions, so-called polynomial and exponential functions. And it seems like you cannot really simplify any further. So a product of two functions means that we need to use the product rule. So let's bring the product rule. U dv plus v du. So I'll let u be x squared and v be e to the x. Just easiest that way. So we write u as x squared. Differentiating e to the x, we get e to the x according to the formula, plus v, which is just e to the x, kept the same. So we need to differentiate x squared, which is a polynomial function. So we use a power rule. We bring the power down in front and then the power minus 1. So that is just power 1. We don't need to write the power 1 there. We could simplify it a bit further. So we factor e to the x out, and inside we have x to the 2 plus 2x. So far so good, right? Next, a little more challenging. Here we have ln x here as the top part and x here as the bottom part. And that is the quotient between two functions. You could look at this as ln x times x to the minus 1, but dealing with a power of a negative number can be tricky at times. So let's use the quotient rule. So we're going to do v du. So v, right, v du. Differentiating ln x, we get 1 over x. I'm just going to write 1 over x here first and simplify later. Minus, don't forget, u dv. So u is ln x. dv, we differentiate x, so we get 1. Or divided by the bottom squared, which is x squared. Simplifying the top bit, the first term right here can cancel to 1. So I have 1 right here. This is just a ln x and is 1 minus ln x, or divided by x squared. Still quite okay, yeah? Next, we have a different function here. So we gotta differentiate sine of x squared plus 1. Well, if you look at the biggest picture here, it is a sine of something. So here we have the outer function and the inner function. There is nothing more suitable than the chain rule. So let's use the chain rule. The way you do chain rule is to differentiate from the outside in. And for every time you get the derivative, you have to keep multiplying outside everything. So the first step is to differentiate the outermost function. Differentiating sine, we get a cos. But we're not going to do anything to the inner part yet, so we gotta keep it the same as x squared plus 1 here. We go one layer inside, we see x squared plus 1. So to differentiate x squared plus 1 is just a normal power rule differentiation. So differentiate x squared, we get 2x. Differentiating 1, we get 0, so I don't need to write. Conventionally, if we want to write to avoid confusion, we should put the 2x in front because it is not part of the angle. And then write cos x squared plus 1 like this. And that's still okay, right? How about this one? We have ln of sine of 3x squared. Well, this is very nested. So you have the outermost function being ln. And when I say that, you probably realized already that this should be a chain rule. So we have the first layer being the log function. The next one is sine. The next one is polynomial. Again, when we do chain rule, we need to differentiate from the outside in. Differentiating ln, we get 1 over everything. We got to keep everything inside ln the same first because this is a chain rule. And then when we go one inside layer, we see sine of 3x squared. We need to differentiate from the outside in again. So we differentiate the sine function here, which should give us a cos, where the inner part is still kept the same for this. So that is just 3x squared inside. Going another layer inside, we see a polynomial function, 3x squared. So we're going to use a power rule there. Bringing the power down to multiply in front, we get 6. The power minus 1 is just x to the power of 1, so don't need to write that. That is just done. If we want to simplify all this, we see that cos over sine is a cot. So I can write cot of the same angle, 3x squared times 6x. So far so good, right? Let's jump to the challenge. Here we need to differentiate this expression. If you look at the biggest picture here, it is a product of this whole expression with sign of something. So the outermost operation here is a product of two complicated functions. And that means we need to start by using the product rule. So again, I'm going to make this part u for the first time and this part v. Let's bring the product rule here. So I'm writing u in the parentheses, kept the same, multiplied dv. To differentiate v here, which is seemingly a nested function where the outermost function is a sign and the inner part is just e to the x squared. So differentiate that, we need a chain rule. So we differentiate from the outside in. So differentiating sign, we get a cos of the inner part kept the same first. And then we go one layer in, we see e to the x squared. So we need to differentiate that and multiply outside everything. Differentiating e to the x squared, it is another chain rule here where we need to differentiate an exponential term. So differentiating an exponential, we get the same thing, e to the x squared. But then we go another layer inside, we're going to see its power being x squared. So differentiating its power of x squared, we get 2x and we multiply it outside as well. And that is just the u dv part. The next part is v du. So v kept the same, we just write down everything. Du, we need to differentiate the first part here, x squared plus e to the x. Well, because this is the sum of two functions, when we differentiate this part, we need to distribute the operation. That means we need to differentiate separately. So differentiate the first term, we have 2x, and then differentiate e to the power of x, we get the same thing. Don't need to use any chain rule there. And that is just it. It seems like we can't really simplify that much, so we could leave the key result like that. Let's try the last one here. Again, looking from the biggest picture here, we have a quotient of two parts, where the top bit is some square root function, whose inner part is a polynomial function, and the bottom bit is just simply e to the x. And yeah, you can use a quotient rule, because it's a quotient of two functions. So let's bring the quotient rule here again. So the bottom bit being v, first we need to do v du, so I write v here, kept the same. To differentiate the top bit, let me change it to an index form, x to the 4 plus 3x squared all to the power of 1/2. So to differentiate that, seems like we have the outermost function where we need to do the power rule. Differentiating from the outside in again, we bring the power of 1/2 down. The inner part is kept the same first, where the power will be subtracted by 1. So 1/2 minus 1, we get minus 1/2. But we're not done, because we need to go one layer inside. Going one layer inside from the power, we have the polynomial function, and we gotta differentiate that inner part as well. So differentiating that, put in parentheses, we have 4x to the 3 by differentiating x to the 4, and plus differentiating 3x to the 2, we get 6x by the power rule. That is the first part done there. Now the second part on the numerator, we keep the top part the same and differentiate the bottom part. Differentiating the bottom part is still e to the x, because that is what we get after differentiating e to the x. The top part being the same as x to the 4 plus 3x squared all to the power of 1/2. And all that will be divided by the bottom part squared, which is e to the x raised to the power of 2. So we can write it like e to the power of 2x using a law of exponent. Should this be required to be simplified, I would just look at the common terms here, and that is to have this term and that term and e here. So if we take e to the x out with x to the 4 plus 3x to the 2 to the power of minus 1/2, and big parentheses here, we have what's left inside in the first part, which is 1/2, and this term right here, 4x to the 3 plus 6x. On the second part, after being factored out, so we should have a power of 1 left in that term. So I'm going to write just x to the 4 plus 3 to the x squared, power of 1 like that, closing the parentheses. And of course, the division of e to the power of 2x, we can just rearrange it so that it is pairing up with just e to the x there, because that will be simplified later. And if you try to tidy up and simplify the terms a little more, you'll get something like this. And that was it. How was everything? I hope that you have built a stronger foundation of understanding differentiation now. Again, feel free to check out all the videos on differentiation that I have made in the playlist. If you think what I do here is useful to you, please subscribe the channel. And you can rest assured that there will be more to come. Don't forget guys, keep studying. Bye.